Ladies and gentlemen, thank you all very much for coming to our public lecture tonight. Before we start, I'd just like to run through this emergency information for you, which is be aware of the exits. So there are 2 exits at the back and 2 more exits here at both sides. If there is an emergency, follow building residents, which is essentially me and a few other people you will see here who will basically go back through the building and out there, or if necessary, out here. Earthquake, I think we're all familiar with this, and if there is an emergency, the number to phone is from inside here, 9911. So there we go. Now, tonight we are delighted to have our guest speaker who, for the first time in this now getting on for 3 years history of our public lectures, we've had a speaker who's flown in specially from Europe to give this talk. That Sarah has just come in from Geneva in Switzerland, where she is currently working on the Atlas experiment on this incredibly exciting, for anybody involved in particle physics, the new project, the Large Hadron Collider, the LHC. That I was lucky enough in 1991, I think it was, to be involved in organizing the first conference when we started talking about the LHC in Geneva. And now, how many years is it? 16, 17 years later, it's nearly at the stage where this machine is going to start working. There's tremendous excitement about this. We're very lucky to have Sarah with us. She's a dazzling young physicist. She did her first undergraduate work at Harvard, then got a doctorate at Rochester University, and we're delighted she's now working here at SLAC. When I say here at SLAC, that's actually wrong. I think she spends virtually all her time in Geneva. So basically she flies from California to Geneva, which can't be that bad. So after the talk, Sarah will answer questions, but also there will be other people lurking around at the top wearing these special identifying caps who are other physicists who can answer your questions about tonight's talk. So everybody, please give a very warm welcome to Sarah Demers.
Thank you. All right. I think I'm turned on. Thank you very much, Neil, and thank you very much for coming tonight. It's always fun for me to have a chance to talk about particle physics. What I'm going to do is actually start with a few definitions just to get us all in the right frame of mind in terms of just how extreme this field is. And then I'm going to talk about the present state of our ideas in particle physics, talk about some of the gaps that we have in our ideas that are really the main motivation for why we have this new machine, the Large Hadron Collider. I want to talk a little bit about how the machine works and what makes it different from what's come before, and also give you a sense of what kinds of physics we hope to explore with it. So starting out with some definitions. When I say definitions, I don't want you to get too depressed. I'm talking about one-syllable words here. Small, big, fast, and cold. Particle physics really is a physics of extremes. And I want to show you in some of the ways that's true. First of all, particles. We're talking about particles. What exactly is the size of a proton? You look at this number, you have a decimal place and 20 zeros, and then a 1, that many meters across. I don't know about you, but after I get past about 3 or 4 zeros, my eyes start to cross and it loses a little bit of meaning. I think we can get some sense of how tiny a scale we're actually talking about by some analogies. So what I'd like you to do is picture a raisin in the middle of a football stadium. So you put a raisin down, think about how many steps back you have to take before that raisin actually disappears from your view. When you're sitting in the top of the bleachers, how tiny is that raisin compared to where you are? And I mean, you obviously can't see it at all. That's the difference in scale between a proton and an atom, is that raisin inside that football field. If you want to get from a proton to something that's a large normal object, like a bottle of Sprite or an apple, you have to do quite a bit more in terms of a huge difference in scale. The difference between this proton, the size of the proton, and the size of something like an apple is the difference between the size of a raisin. So picture how many raisins you can fit between the distance between the sun and the earth here. So that's an absolute huge difference in scale. And you note that I'm talking about something really, really tiny, but to understand how tiny it is, I actually have to go to astronomical scales. So when we talk about particle physics, we're talking about something way beyond what we can see and what we're used to dealing with in everyday life. Ironically enough, we don't only deal with the small, but we also deal with the big. When I was thinking about big, what's the biggest experience that I've had in my life, aside from staring out at the night sky, I would say it's looking out at the Grand Canyon. When I started working for SLAC, I was based in Rochester, New York, and had the chance to drive across country. And my husband and I stopped at the Grand Canyon and caught a picture at sunrise. And the Grand Canyon is just absolutely vast. It was one of the biggest feeling experiences I've ever had. If I put a map here of the Grand Canyon, it's a nice free map from the Park Service, and I draw on this big machine that I'm going to be talking about tonight, just to give you a sense of scale. My husband and I are sitting on the south rim here, looking out toward the north rim. This is the south rim of the Grand Canyon. You can see this is a man-made machine here. We couldn't fit two of these side by side inside the Grand Canyon. So the very biggest thing I can think about on Earth is on the same scale as this machine that we're using to detect things that are so tiny that we need to talk about raisins in the distance between the sun and the Earth to understand. Okay, fast. If you're like me, when you think of fast, you think of the SLAC relay team. We actually had our first event last month at CERN, May 2007, and this is me. I was actually the captain. I drafted the team, so I'm very proud of us. I'm not going to tell you what place we came in out of 82 teams, but we had tough competition. These are some faces. Actually, Charlie's here tonight. He's going to be wearing a hat, so you get to talk to him. I caught some of us running. We were fast. It was a 1,000-meter leg, 800-meter, 800, 500, 500, 300, very fast. But on the scale of particle physics, I'm afraid that the SLAC relay team at 10 miles per hour was basically standing still. In terms of particle physics, our tiny, tiny protons whizzing around this gigantic machine get moving up to 670 billion miles per hour, which is about 99.99999% the speed of light. And dealing with that, you can see that I've gone everywhere from standing still to this very fast SLAC relay team, all the way up to a shuttle in orbit, 17,000 miles an hour in relation to the Earth. And we're all crowded way, way down here, where we have our protons whizzing around all the way up there, very close to our natural border of the speed of light. And the last extreme that I want to talk about before I dive into the standard model of particle physics is one that I think you're going to have the most difficulty understanding. I have to tell you, the LHC magnets are going to operate at 1.8 Kelvin. Kelvin is the scale that's developed to be zero at the temperature that we believe is the lowest temperature that you cannot go below, absolute zero. What that means is negative 459 degrees Fahrenheit is the 0 point. Up 2 degrees, we're talking negative 455-ish, negative 450 degrees Fahrenheit for where the LHC magnets are going to operate. I have a thermometer up here to help us understand this. Room temperature is right at this point, 72 degrees Fahrenheit. What worries me about this crowd is I've been here a total of like 4 months, I think, if you count all of my visits back and forth, and I swear it hasn't gone out of this range, 60 degrees to 80 degrees Fahrenheit, until last week, when I think it hit 85. It was very warm. We were all very disturbed by this at the end of last week. Now, my family has a better shot at understanding cold, because my parents right now are in Lake Placid, and they had a week this past summer at negative 40 degrees Fahrenheit. And here's a picture of my brother digging out his car in Burlington, Vermont, which is right across Lake Champlain from Lake Placid. But even the folks from Lake Placid have quite a ways to go to get down to understanding what the temperatures are of the operation of the LHC. This picture, by the way, was taken by someone right outside of CERN in France a few winters ago. Okay, so just to give you a sense of what we're talking about in terms of extremes and in terms of scale. And now I'm going to ask you to do a little bit of work with me in terms of understanding where we are in particle physics. This first statement here is, it's particle physics specific, but it also applies to physics in general, I think. Our goal is really to categorize the fundamental building blocks of nature and the forces that govern their interactions. If you extend this to all of physics, when we talk about interactions, I have here a picture of a nucleus splitting up into smaller pieces. I have a picture of a football game, and I also have a picture of Saturn. Just to give you a sense of when I talk about interactions between things, I'm talking about interactions between particles, interactions between people, interactions between planets. That's really our goal in physics, is to understand how all of these interactions work. Particle physics adds something special to this, though, with the idea that there is no such thing as a magical action at a distance, and the interactions happen through particle exchange. What this means is, if someone, for example, is sleeping in the 8th row of the lecture, and I want to interact with that person, I can't just think to myself and magically wake that person up. There has to be some kind of an exchange, right? Unless that person wakes up by themselves. So if I had a basketball or something, I could throw it at the person and wake the person up. I could even yell at the person. But even the act of yelling is actually particles interacting with that person's eardrum, making that person's eardrum vibrate, right? I'm creating those pressure waves that are going to that person's ear. So the idea is anytime you have two particles interacting, there is a particle exchange going back and forth. And the basketball analogy is actually pretty good, because you can think about that basketball going back and forth. You have to imagine that basketballs can both be repulsive, so I can throw a basketball at someone and they rebound back. It can also be attractive, because we have attractive forces in physics. So we have to have a different kind of basketball that I can throw and make somebody actually come toward me as a reaction. Excuse me. Okay, so every interaction that we have, macroscopic, microscopic, we believe we can break down into 4 forces. I think I've lost my pointer. I've lost both pointers. That's okay. You're kidding. In your bike bag? This is a very prepared person. Okay. What's this? No, there is a communication. There's a communication. Right, okay, I see you're right. Case in point, right? Broken? Is that what you mean? You're saying my remote is action at a distance. I'm actually okay without the pointer, I think, for a while. Okay, so 4 forces, like I said. Gravity. Gravity we understand very well on a macroscopic big picture scale. We understand it so well we can actually send rockets around and have them land where we want them to land for the most part, right? We don't actually have a microscopic understanding of gravity, but we're so bold about this idea of particle exchange that we've named the particle, the graviton. I don't know if you've heard of it. We haven't found it, but we think it exists. We believe there is a particle that lets this planet know that this planet is there. There has to be something going back and forth between them. Thank you very much. Okay. Yes, excellent. Thank you very much. No, it's excellent. Okay, so that's gravity. Like I said, we haven't found the graviton, but we do think there is that object that lets the planets know that of the presence of another planet. The second force is electricity and magnetism. This is another one that we're as familiar with as gravity. Maybe not familiar with lumping the two of them together the way I have. Electricity, electric charges, shocks, lightning, we've all dealt with that. Magnets, we deal with in refrigerator magnets, but you've also played around with magnets, I'm sure, in other areas. It turns out that you can create magnetism, a magnetic field, by moving electric charges. So these two things are very deeply linked, and we understand them well enough to be able to put them into the same category of a force. There are 2 other forces, and I'm going to act on the assumption that you're not familiar with them, and if you are, this is just going to be a review. The third force is the strong force, and the fourth force is the weak force. So like I said, I'm going to act on the assumption that we aren't familiar with these 2, and I'm actually going to punt on talking about them now and come back to them in a few minutes. So I owe you an explanation on the strong force and the weak force. When we move to the standard model, like I said, we have an idea, the graviton, about this 4th force, but we only encompass 3 forces in the standard model. And we also have 12 fundamental particles. I'm going to throw them all up. Nice to highlight a couple of them that were actually discovered at SLAC. There are quarks and leptons. I'm also not sure if you're familiar with those names. My mother used to get excited when I would come home and talk about particle physics. She thought we were very creative in terms of our naming schemes. So we have 6 quarks and 6 leptons, and I have them all listed here, and I'm going to talk about them a little bit. I want to just go through and mention up, down, charm, strange, top, bottom. We have names for each of these quarks. You also will see them referred to in literature as just the first initial. So the up quark you'll see as a U, and the charm quark as a C. And when I have that, I'll try to point it out and remind you. We have a bunch of leptons and the electrons in here, which I think we're familiar with from some high school chemistry or some high school physics maybe. And then also the tau and the muon and some neutrinos. And then we have our three forces over here. And I told you that each of those forces can only happen through some kind of particle exchange, and I've listed those exchanges right here. You'll notice for electricity and magnetism, the exchange particle is the photon. That's the particle that's going back and forth for the electrical and magnetic force. And I haven't talked about the strong or weak force yet. So let's back up to something that we're more familiar with, and then work our way from there. I'm pretty sure you've seen the model of the atom with protons, neutrons, and electrons. The idea is we have our protons and our neutrons crammed inside into the center in this very compact and massive nucleus, and outside it we have our electrons orbiting. Experiments were done, early experiments in particle physics, that found that the proton was not a fundamental particle. So let me just say, I say fundamental quite a bit, what I mean by fundamental particle. If you think about a Lego set, I have a bunch of Lego blocks. Each of those blocks is something that's fundamental. I can put them together and make different objects, but I can't break up that smallest block unless I have very good teeth, right? But no, you're not supposed to. That's a fundamental block, is that smallest Lego block. It turns out, we thought for a while that protons and neutrons were fundamental blocks, couldn't break them up, nothing inside. It turns out there were actually 3 quarks inside each proton, and 3 quarks also inside the neutron. 2 up quarks and 1 down quark for our proton, 1 up quark and 2 down quarks for our neutron. By the way, when we have combinations of quarks like this, we call them hadrons. So now you know where that Large Hadron Collider name comes from. It's a combination of quarks, like this. The proton, an example of a hadron, we're colliding protons in that collider. Okay, so we can do this. We can change our protons, neutrons, and electrons for up quarks, down quarks, and electrons. Electrons maintained as fundamental particles, didn't break them up into other things, and up quarks and down quarks were added, and they make up the protons and the neutrons. We have quite a list to get to our 12 particles of things that we haven't explained here, right? We still have 9 particles to deal with, and then we still have these 2 forces. And I want to attack them category by category, and the first one I want to talk about is the neutrinos. So there are 3 neutrinos in the standard model of particle physics. They're around us, they're going through us, and they're even coming from us all of the time. I like to think about these numbers. 4, and this isn't fair because I talked about how it's hard to use big numbers and take anything out of it, but 400,000 billion neutrinos from the sun pass through you every second. During the daytime, they're coming from your head through your feet, and at night, they're coming from your feet. They go straight through the earth, up through your feet and out your head. Or hopefully at some point you lie down, right, and they go straight through your body, depending on your job, I guess. Okay, but what's also interesting is we emit neutrinos, about 340 million neutrinos every day, because we have potassium in our bodies. The fact that there are so many of these things around and they're never a problem for you should make you not too alarmed that you don't hear about them in everyday life. They're very difficult to detect. They don't interact with us very often at all. So I think it makes sense that neutrinos aren't something that are part of our general consciousness. This is an experiment right here that was built to detect neutrinos, because we have seen them. We've actually detected them. This is a great picture from the University of Tokyo. I don't know if you can see these guys in the boat, but what's happening here is it's a huge cavern full of water. Neutrinos come in, and they decay inside. You can detect that decay with all of these what are called photomultiplier tubes. So this is a picture of them very slowly filling up this tank, and these guys go around in this boat and they shine the surfaces of the photomultiplier tubes. And I'm not going to tell you the story because it's too depressing of the time when they got the pressure calculation wrong and they started to fill it, and these things started shattering, and there was like a chain reaction of shattering, and it was, would they lose like 1.5 years? Charlie, how much time? I don't know where he is. Anyway, it's really tragic, so we'll move on from that right now. I said that this isn't part of our general consciousness, neutrinos, because we don't interact with them, but John Updike did write a poem about them. I don't have time to read the whole thing, but I hope you'll Google it. It's kind of a fun poem. I want to point out that there are a couple of couple of mistakes in it. Or at one point, we really did believe that neutrinos had no mass, but now we believe that they do have a very, very, very small mass. And it isn't really true to say that they do not interact at all. They do interact a little bit. But that's neutrinos. We've seen them, but it makes sense that it's very difficult to see them and that they aren't around. As much as they're around, it's hard for us to notice them. In terms of the quarks and the leptons, the only quarks that we have that are in the atom that I've talked about are up and down quarks for the proton and neutron, and then the electrons. And everything that's around us is actually made up of those up and down quarks and electrons. And the only time we have access to these these other particles, the other quarks and the other leptons, are from cosmic rays coming in from the sky, very high energy cosmic rays. And I want to walk you through this slide. There's a ton of information on this slide. What it does is we have a scale of time, temperature, and energy here. We're starting at the Big Bang, and we're moving from the Big Bang to the present day on this side of the picture right here. So we are moving forward in time from the Big Bang. We're moving down in temperature and down in energy. The idea is at the time right after the Big Bang, we had not just up-down quarks and electrons around, but all of the fundamental particles around. And as the universe cooled off and as time passed, we were left with, in this present day, only the up and down quarks and the electrons around us in terms of the matter. What's interesting also, I don't know if you can read these things up here, but what you can see is listed different accelerator experiments. So here we have CERN and SLAC, CERN, LEP, and SLAC, and then Fermilab's Tevatron, and we're inching closer and closer to the Big Bang here. You can see the closest to the Big Bang in terms of these experiments is the Large Hadron Collider at CERN. These little movements closer to the Big Bang represent huge differences in terms of energies and physics reach. So what we're doing in some ways by building this machine at higher energies is getting ourselves closer to the Big Bang when we had access to these more massive particles. So the particles other than the up and down and the electron. Okay. Now, I punted on the strong force and the weak force earlier, but my goal is, within the next 2 minutes, to make you absolutely outraged without the existence of a strong force. I think this can happen. Electrical charge, we're familiar with, right? We have opposites that attract, and we have likes that repel. If I have a negative and positive charge, we know that they attract, and this even makes its way into pop culture, our understanding of opposites attracting and likes repelling. Okay. Let's look at the nucleus. I think the best way to form a really stable atom is to take a lot of positively charged particles and throw in some neutrally charged particles, but a lot of positively charged particles, cram them all together into a tiny, tiny, tiny space. Remember we learned how tiny that nucleus is at the center of the atom? Do you see a problem with this? Positively charged particles, they want nothing to do with each other, very, very strong repulsive forces, and we're all just cramming them into the nucleus. When I think back of myself sitting in high school physics and chemistry and just writing down, yes, that's right, good, protons and neutrons at the center, I'm always really disappointed in myself that I wasn't just outraged and standing up and saying, that doesn't make any sense at all, how you can cram all those positively charged particles together. So, do you agree with me there's a problem there? There's something missing. It's not stable. That's where the strong force comes in and saves the day. It's very nice that the particle that's exchanged in the strong force is called the gluon, okay? It works as glue. The strong force is an attractive force. It's the force that the quarks feel on each other that binds the protons and neutrons together. But more than that, if I have two protons here, you can see they're both positively charged. They're repelling each other, but the quarks inside them have strong forces. There are gluons being exchanged between these particles, and the strong force is binding these things together. And there's a nice graphical picture of this. The strong force is very strange. It's unlike other forces that we're used to dealing with. I think the best explanation of it is like a rubber band. If you have particles, quarks, that are very close to each other, there isn't a lot of force on them. As they start to pull away, the force increases and increases until they're yanked back. So it's almost like this springy motion that you can have inside where these particles are bound very tightly together. As soon as they start to try to escape, they're pulled back. So it's really a rubber band force, and it gets us out of this horrible predicament of cramming all the protons and neutrons together at the center of the atom. The last force is the weak force. I told you that at the time of the Big Bang we had all the particles, not just the electrons and up quarks and down quarks. We had muons and taus, those other heavier leptons. If we didn't have a way for those particles to decay and change into other particles, we would still have all those particles around now. The weak force is the force that allows these fundamental particles. This is an example, I'm sorry, I've used the Greek muon here. This is a diagram of a muon that's decaying to an electron and 2 neutrinos, where these V's here represent the neutrinos. Now, this muon does not have an electron and 2 neutrinos inside it. The weak force actually allows this decay to happen, where I have this particle changing what we call flavor, changing into a different particle, a group of particles. The weak force is why we only have up, down, and electrons around with us. And I know this isn't it's not as, I don't know, what's this? Intuitive, yeah, right. I mean, you aren't outraged without the weak force, maybe, until you try looking for those other particles and not seeing them. Okay, this is the only plot that I have in my talk, and it's not a good plot. It's actually really not a good plot, but I have it in here because it's a plot for my thesis, and it makes sense in the context that it's in. And it's to tell you that the particles that are the exchange particles for the weak force are the W and Z bosons, and that's another one that my mother liked very much when I told her about them. These things seem, you study particle physics, but it seems very unreal. I remember when I was in graduate school, just starting out graduate school, I was working on an analysis, just learning how to do an analysis, made a plot from some simulation that I was working with, and I had this really crazy shape in the plot. I expected something that looked nice and flat. I had this really crazy looking bump in my plot. I went running to my advisor and I said, something's really strange going on. It's a bump, I don't expect a bump. And he looked at me and he said, Sarah, that's the Z boson. And I said, you're kidding. It's real. You know, these particles, there really is evidence for these particles. And this is one of my early plots of making that realization myself after all this time on the computer, because you can't see these particles. It's easy to forget that they're actually real and out there. Okay, so that was your lightning intro to the Standard Model. Now I want to tell you about some problems with it, and we've already talked about some of them. We've hit on some of them. Gravity. We have this great understanding of gravity and general relativity, and we can, like I said, land these rockets in different places. But the graviton hasn't been seen, and we don't have the gravity in the Standard Model. We do not have a microscopic picture of gravity. And you could say that's really embarrassing. I mean, it's gravity. We all know gravity exists. You jump, and there's evidence for it right there, right? It's actually not as embarrassing as it might seem, because gravity is an extremely weak force. We don't think of gravity as weak because planets being attracted to each other on that scale doesn't seem very weak. But if you think about it, this is one of my coworkers, Klaus, likes to use this analogy. You have a magnet, just a bar magnet, and you put a nail on that magnet, and you allow the nail to be held up. Basically, a little bar magnet can hold up a nail. You have the entire Earth pulling with a gravitational force on that nail, but that one little bar magnet is enough to hold it up. That gives you a sense of how weak gravity is compared to electricity and magnetism. The entire Earth can't pull that magnet. Or a refrigerator magnet is another example. You have the entire Earth pulling on that little piece, right? But that magnet has enough strength to hold it up to the refrigerator. So we don't have to be as embarrassed at the fact that gravity isn't in our model, but we certainly would like to. I mean, we don't have a complete model without having gravity included. So this is a problem, but it's understandable that we're there. This is more legitimately embarrassing, maybe. This right here is a picture of an iceberg. It represents an iceberg. You know how in an iceberg, only about 10% of the iceberg is above the water? So you look at something above the water, you don't realize there's this vast iceberg underneath it. It turns out that we think that only about 5% of our universe is explained by what we have in the Standard Model. We have two other categories here, 25% dark matter, 70% dark energy, and I'm going to talk about both of them briefly, that are not covered by our Standard Model. So I think maybe it's a little optimistic to call this a gap in the Standard Model, 5%. Yeah, okay, so this is a problem. I mean, we certainly would like to, yes, sir?
If neutrinos are given off by the stars in copious quantities, and they're not absorbed except very rarely, don't they pile up?
Neutrinos, don't they pile up? But pile up on what? The question was, do neutrinos pile up?
They float around in there.
They just keep going is the issue. They don't get stopped. They aren't decaying. Yeah. We can talk about that more a little bit later even. But what I'd like to talk about right now is this dark matter and dark energy sections, the 25% and the 70%. This is a picture that a group of scientists drew up looking at a region of sky. What they did is they saw that there were clumps of gas out in this region of sky. The clumps of gas were held there by some gravitational force. There had to be something keeping these clumps of gas there. But when they looked out for what was the reason behind these clumps of gas being there, there was not enough matter there to explain it. There wasn't enough there to hold the clumps of gas. Does that make sense? So what are these clumps of gas doing there? There must be something holding them in place. They went through and they mapped out all of these light areas, or where they came up with where the dark matter needs to be, in order to explain what these clumps of gas were doing out there. So what is this stuff? It's not what's in our standard model. But I'll talk later about how the LHC might help us understand it better. Dark energy. I don't know if you're familiar with dark energy. The experiment a couple years ago where it turned out that the universe was expanding at an accelerating rate. Do you remember hearing about this? It was actually in the New York Times. It was one of the results that makes it, into the normal press. So this is a nice example of that, or illustration of that. You have somebody blowing on a balloon. When you blow into a balloon, and this was actually done, this and the iceberg were done by somebody at SLAC, Nicole. You blow in the balloon, you have every point, you pick any 2 points in the balloon. When you blow into it, those 2 points are moving away from each other, right? So it's a nice explanation, or a nice way to visualize this, everything in the universe expanding away from everything else. But to expand at an accelerating rate really doesn't make any sense, because the forces acting on these galaxies are gravitational. There should be at least slowing down. They should be pulled together. If you start this thing going, there's nothing to explain why these things would have rockets on them and be speeding away from each other, right? You have gravity. It should either be slowing down and then come back in. At least at any point in time, they should be slowing down in terms of their escaping from each other. So dark energy is this idea that there's something giving this energy for these galaxies and all this matter to be accelerating away. Okay, I think this is my last gap slide. We've talked about how we don't really understand gravity in the standard model, but we do know that particles have mass. It's interesting that the particles that we've measured have a huge range of masses. We don't really understand why the particles that have mass, and why there's such a huge range of masses of the particles, and that's something that we'd like to understand. So that's another thing that we're keeping in mind as being a problem with the model. Okay, this right here is a nice, basically standard model squished into one block. So we have our quarks, just as a review of everything in the model. Our 6 quarks, which as I mentioned, they can be named, this is up, down, charm, strange, top, and bottom, where all of our matter around us is made of up and down. This is our lepton block right here, where these V's represent our 3 neutrinos. Underneath we have our electrons that we're familiar with, and then the muons and taus. Over here we have our force carriers listed. You might recognize the W and Z bosons for the weak force, the G, which is the gluons for the strong force, and then gamma for the photons of electricity and magnetism. So it's actually pretty compact. You can get all of these particles on here with the force carriers. That's the standard model. Now, you have some sense of where we are in particle physics and some sense of the real problems we're facing. This is the tool that we hope to use to go after some of those problems. I think I've mentioned this, but just to make it more clear, in this slide here, we talked about the accelerators getting more and more energetic, bringing you closer and closer to the Big Bang. I just want to mention that Einstein did give us a relationship between energy and matter. It turns out that if we have 2 protons, and they're moving very, very quickly with a lot of energy, and we have them collide, we can create particles that are more massive than those protons. So we can actually turn that energy into massive particles that we can study. And also it allows us to break the very strong bonds of that strong force holding the quarks together at these very high energies. So the Large Hadron Collider. My alternate title was the biggest refrigerator in the world. This is a picture of it. It's located on the border between France and Switzerland. And this right here, you can see the Alps. The collider, the machine itself, is actually 100 meters underground. like this quote from Young Key. She's a physicist at University of Chicago, and she's a deputy director of Fermilab right now. This right here represents the standard model that we have right now, our current understanding, and how we hope to use the LHC to actually increase our understanding. Some people, I've actually read on blogs recently, when I was trying to find pictures for this talk, I came across some blogs that talked about how we're trapped by the standard model. We must break these bonds. And so I thought, okay, this is a healing slide. We'll have the key come in and help break the bonds. There are people very upset about this. But I really like Young Key's quote, how we are explorers and we will never give up. I thought that was cool. Okay. What I wanted to show you was just a map so you can see what the border looks like between France and Switzerland here, overlaid with the collider itself. So you can see that most of the collider is actually in France. And this joke gets really old at CERN, but we do tell it all the time about how it's a good thing that the protons don't need to have the same paperwork that we do when they cross the border. Because, I mean, the thing is, when you go into the CERN site, when you enter it, which is right around here, across the street from the Atlas detector, you go into the site, and then you could be in France. One of the restaurants is in France, and one of the restaurants is in Switzerland, so you need papers for both, you know. You need to make sure that, and the protons are lucky enough to avoid that. This is a nice diagram that actually shows you how things really look. This collider is 100 meters below ground. And here's a zoom in on one of the detectors. And actually, let me go back. Oh, okay, no, not quite yet. Before I keep talking about it, I want to show you a video. Okay. That will show you what this machine basically aims to do. All right. So this is a proton, or a bunch of protons. You can, I hope, see how what's happening is it's going through a series of accelerators. Can you see these two protons going around? They get injected into the LHC, one in one direction and the other in the other direction, and they're accelerated in the LHC. So through all these steps, they're accelerated. And then once they're at the right energy, these they're actually bunches of protons, are made to collide in the center of a detector, and you have these collisions come out. So that's the goal. And you might ask yourself, and I wonder if I've missed a slide. I haven't. Okay. You might ask yourself how we accelerate the protons, because that's what this machine does, the collider. It in a series of accelerators makes these protons go faster and faster. We start out just with general hydrogen. You start out with a hydrogen atom, and you can get rid of the electron, and you're left with just a proton. And then you want this thing going very, very, very fast. How do you do that with a proton? And I like the analogy of the way this works with gravity. So, how is it that you would accelerate in a gravitational field or with a force of gravity? And I have an example of this with this guy, and I don't want you, this is not a morbid talk. He has a parachute. It's going to open. Don't be alarmed. We know that the longer he falls, he's walked off this building or jumped off the building, the longer he falls, the faster he's going to be going, right? If it's a 10-foot jump, he's not going to be going very fast at the end. But if we're talking about 100 stories here, he's going to get going pretty fast. Now, you've probably heard of terminal velocity. He's going to get going so fast if he's jumping from 20,000 feet, and then he'll stop getting faster. And that's because of air resistance. It's actually everything is particles. It's particles in the air colliding with him that are slowing him down. But if we put him in a vacuum, this guy would actually get going faster and faster in his falling until he approached the speed of light, if we had him in this gravitational field long enough. So that's what we want to do with our proton. We want to have our proton under a force, a strong force, for a long time. So how do I get my proton to accelerate? I mean, I certainly could use gravity because it has some mass, but the proton doesn't have very much mass, and gravity isn't a very strong force. Electricity and magnetism is a much stronger force. I know that I can get my proton to move because I can put positively charged particles here that repel it. These positively charged particles make this proton want to go in this direction, and I can have negatively charged particles here that attract it. So the proton wants to go in this direction. In the same way that this guy, under the gravitational force, will keep accelerating, as long as I have him under those conditions, my proton will keep accelerating as long as I have it under those conditions. The longer we keep that proton in our electric field, and the stronger we make that field, the faster we can get it to go. That's really the heart of why you have a circular accelerator. You do a lot of work to have a very strong electric field. It would be really a shame to only see that proton once in that field. But think about if you could get that proton to circle. As it's circling, it's in your field longer and longer and longer, and it can be getting faster and faster and faster. So you can buy yourself a lot more time with a proton if you get it in a circular accelerator. The problem is you then have to make sure that you can bend the proton. And that's a huge complication, but worth it in this case. So we know that we can bend, and I don't know if you know this or if you're familiar with this, but you probably learned it at some point, maybe in physics, maybe not. If you have a proton that's moving along, and you put it in a magnetic field, and here I have, just in this area right here, a magnetic field that's going into the screen, for example. So you could think of this being created by a bar magnet or a set of magnets, however you want to picture it. My proton actually is going to bend under that magnetic field. We play a very tricky game where the stronger you have the field, the more you can bend on, and the more you can bend the proton, the smaller you can make the ring. Okay? So if you have a very, very, very strong magnetic field, you can bend your proton in a very, very small circle. There's the other side of the picture. The faster you make the proton go, the more you have to give a force to make it bend in that same amount. So you can imagine, as you crank up the speed of the proton to faster and faster and faster, you have to crank up the strength of your magnets to keep this thing tearing around inside that circle. The size of the LHC is actually limited by the strength of magnets that we have access to. If we had stronger magnets we could make, we could have a smaller ring at the speed of light. But the fact that our magnet strength is what it is really determines that, that balance in the LHC. So the magnets are such an important part, I thought it was worth having a couple slides on them. Over 9,000 magnets in the LHC. And this is the part that has to be very, very, very cold because it's superconducting magnets. 1.8 Kelvin, actually it might be closer to 1.9 Kelvin where these things operate. And I don't know if you're familiar with cosmic microwave background. If you go out into space, the temperature is like 2.5 Kelvin. So we're actually colder in the LHC than we are out in the middle of nothing in space. And people have talked about, oh my goodness, we're making like the coldest region maybe in space in the universe with this. I mean, who knows really, but potentially in the universe with this LHC. These magnets are extremely complicated, not only because they have to be that strong, but also because you see here we have two beam pipes. You have protons going in two directions. You want your magnets to be able to handle beams going in two different directions of protons. And then you make those beams collide at the point of your detectors, as you saw in the video. And I'll talk a little bit more about that. But at maximum power, this field is 200,000 times stronger than the Earth, the magnetic field of the Earth. And there's a lot of wires involved, enough to actually circle the equator 6 times. So just some more extremes. This is a cool picture. This was actually the first welding connection done in May 2005 inside the LHC tunnel right there. You can see this guy connecting one of the magnets. Okay, so I mentioned we have these two beams. As you saw in the video, we have protons going in opposite directions. But what's interesting to us, once we get them going fast enough, is to make them slam into each other. So we have extremely high energy. We can actually create very, very massive particles and study them in those collisions. And those collision points happen at 4 different places around the LHC. ATLAS, LHCb, CMS, and ALICE. The SLAC group is working on the ATLAS experiment, so that's the one I'm going to talk about when I talk about detectors. And let's move on to look at ATLAS. The first thing I want to do is, before we do that. The LHC is going to collide these protons at these places 40 million times every second. That's actually 25 nanoseconds between collisions. And there is way too much data. There's way too much information coming out of those collisions for us to keep everything. So we're always working with this balance of what's interesting for us. how do we pick up what's interesting in these collisions? This is a huge part of what the SLAC group is working on at Atlas, trying to figure out what is the physics there. I mean, sometimes these protons will sort of skim each other. Sometimes you'll have a very hard collision with a lot of energy. How do you pick out the stuff that you want? And the real reason I have this slide here is because I promised my boss, this was a picture taken of him scratching his head in the Atlas control room. I promised him this would be in every talk. I've had a couple since it was taken, every talk. You get a picture of your boss scratching his head, it's quality. So there it is. He's a good guy. He's not holding it against me, I don't think. Okay. The volume of data, it's worth pointing out, even after we've made these really hard decisions about keeping only the most interesting stuff, the volume of data we're looking at would fill a stack of CD-ROMs 20 kilometers tall every year. I don't know if it's easier for you if I talk in terms of terabytes. We're talking about terabytes and terabytes and terabytes of data and information. How many terabytes? That depends on how much money we get, actually, in terms of how much we can store. Reiner, how many terabytes do you have? 1,000 for a year, 1,000 terabytes? Okay. Reiner is also working on the trigger. A petabyte, you're right, I could even go to a different unit. Okay, so something to keep in mind, it's actually bunches of protons that we have colliding. This is a diagram, it might not mean much from where you're sitting, but this is a nice sort of clean interaction where you have protons coming in like this, and then an interaction coming out. I don't know if you can see, but we have some nice muons that we're looking at. This is the kind of collision where we could look at it, study it, learn about fundamental particles, and get very excited. What we actually see is this picture above. You know, up to thousands of particles that are created every time you have these things interact. You have to pick out what's the interesting stuff, what comes from the collision point that you're interested in. You have up to 25 little collisions that happen when these bunches collide, and maybe you're only interested in one of those interactions. So there's a lot of work that's done with computing, what we call reconstructing the events, these collisions, and finding out what's interesting in them. And here are some pictures of the Atlas detector. It's about 5 stories. Here's a person to show you a sense of scale. These huge things out here are actually toroidal magnets along the outside. We mentioned that magnets will bend charged particles, so we have one way we can learn about the particles that come out of the collision is to bend them. And we can learn about their masses and their charges by seeing how they react to those magnetic fields. Here's another picture. This guy's standing, he's cheating, he's standing on something there. It's more zooming into the center. You can see just millions of optical and electrical signals that come out of the detector. There are more than 2,000 physicists, technicians, electricians, and students, 151 institutions in 33 countries. These numbers are going up all of the time. It's one of the most exciting things about particle physics. If you think about it, there's one place in the world that's going to be at this energy. Everybody from all over the world who's excited about particle physics, and this kind of particle physics is there. I mean, there are other places you can study neutrinos, but if you want to be at the energy frontier in a hadron collider, everybody's there. It's really fun. The detector itself is comparable to the Eiffel Tower in terms of its weight. And this is my favorite slide because do you see these little people? That's a person right there. You can see the 5 stories. This is just one end of the detector, the muon chambers at the end, and the detector goes out in that direction. But you can just see the sense of scale there. Very fun being outside CERN right now because of the things that are transported across the street. This is just a little piece of the end cap of the detector coming in. Yeah. And they got there, and they knew they were going to have to do this. I know they knew, Charlie, they knew they were going to have to do this. But see this chimney right here? It looked really funny for a couple of days because the detector, that piece of it was sitting outside the hall and it actually didn't fit. Their plan was all along to cut out something from the building so they could slide the thing in, but it was actually kind of funny. We all thought, ooh, maybe it's a metric system conversion mistake or something. But no. Okay, so the philosophy behind these detectors is sort of a can philosophy, meaning I have these collisions that happen at the center, and you'd like to understand everything that comes out of the collision. So you want to completely surround it, and like with a Coke can or a soda can or something, get everything that actually comes out you want to catch. And so you match the can philosophy with the onion philosophy. You have your can that tries to catch everything, and your detector itself is like an onion with different layers, where each layer has a specific job. So it will tell you something about certain particles, masses, or energies. On this next slide, I've tried to show you another picture. So I have my protons coming in on either side, and you can see that I have these different colors here for my different layers of detector. If you were a particle coming out of one of these collisions, so I have a collision that comes right here, the particles fly out, hundreds, maybe thousands of particles. Those particles pass through the different layers of detectors, and I have a list of particles here that may or may not be familiar, but what you can see is they all interact differently. My photons, for example, and my neutrons, that's this N, do not interact in the tracking chamber, but they do interact here in the electromagnetic calorimeter. You can start to play games and say, aha, how are the photons different from the electrons? They look sort of similar here, but they're different right here. So you see how you can play these games with different layers of the detector? It's very complicated in some ways, but in other ways, really understandable what the overall goals are. There are a couple of details that aren't on this slide. Muons actually make it all the way out your detector. So what you do is, if you want to find a muon, you have your detector, and then outside you put a bunch of crap, shielding. You try to stop everything else. You make sure that you stop everything you possibly can. And if something actually makes it out further, you say, aha, it must be a muon. Everything else would have been stopped. Neutrinos. We want to know if there are neutrinos in our event. They're important. They can carry energy away. But you don't see them on this list because they don't interact with our detector. I mean, they don't interact with us. So what you do is you say, okay, I had protons coming in like this and colliding. There was no energy or momentum in any of these directions, what you call transverse to the beam. So when I have my collision here and all the particles come streaming out, I can bet on conservation of momentum and energy in this area. So you have a collision like this, like you can even imagine pool balls or something. They come in, they collide, and you shouldn't have any energy produced coming out in this direction. I don't know if that makes sense. But we detect neutrinos because things don't balance out. You say, wait a second, if you have a collision like this, and then all of a sudden all of the particles that stream out come in this direction, you think, where did I get anything pushing me in this direction? There must be something that went over there to balance that, and that would be your neutrino. You didn't see it, but it must be there because everything else comes to this side. So there's a lot of different games. It's very interesting and very fun to play those games with the events inside the collision. So what are we hoping to get with this machine? What do we hope to see? And why do we go through all of that work? Well, the very first thing that we'll try to do when the LHC turns on in 2008 is try to understand more about those heavy standard model particles, the top, bottom quarks, charmed, strange quarks, the ones that aren't the up and down quarks that we don't have around us all the time. I have a picture here of Fermilab, which is different in scale. The Large Hadron Collider is about 5 miles across, in terms of diameter, whereas this is less than 2 miles across. It's maybe about 1.5 miles across, Fermilab is. So we're going to have much, much more energy than Fermilab did at the Tevatron. The top quark was only discovered in 1995. That's the heaviest quark. It's not very long ago. And Fermilab makes top quarks, but not as often as the LHC. At the LHC, we're actually going to be called the top quark factory. We're going to make so many top quarks. We'll have thousands more top quarks than they had at Fermilab. We can understand an awful lot more about particles that we already have in our standard model. Another thing that you might have heard about, the Higgs boson. There's a book written about this by Letterman, The God Particle. This is the particle that we hope will get us out of this question of why do some of our particles have mass, and why do they have the masses that they have? The idea is that the amount, and I have here, this is hopefully familiar, the quarks, the leptons, and then the force carriers. The Z and the W have mass, the photon and the gluon do not. So hopefully we'll understand by how these particles interact with the Higgs boson, how much mass they have. And actually there was a guy, I think his name is David Miller, who won a prize for an explanation of the Higgs boson that I think is really good, and I want to go through it really quickly. This, by the way, is just a cartoon of somebody sweeping in the LHC tunnel the normal particles and the Higgs particles. Okay, so this top picture, there's somebody up here. First of all, everybody's perfectly spread out, right, at a nice cocktail party chatting. This guy whispers a rumor, very interesting rumor, and before you know it, there's this clump of rumor that then everybody's attracted to this rumor and hearing this rumor, and the rumor moves through the room. You can think about different particles and the amounts of mass they have being associated with how interesting that rumor is. That's, if it's a really great room, or you have the entire room that's sort of clumping together a lot of mass, that's like how much these particles interact with the Higgs boson. So that's an idea of how that mechanism will work. But people at the LHC are extremely excited about this, and Fermilab actually is still going after it right now. Okay, another idea that people are really interested in is supersymmetry, also known as SUSY. Supersymmetry. Every particle has a superpartner. So all of the standard model particles that we know, which are represented up here, have superpartners down here. This actually is required by string theory. I don't know if you're familiar with string theory, but it helps us with this quantum idea of gravity. And if there is supersymmetry, it's possible that the lightest supersymmetric particle actually could be our explanation for dark matter. Maybe it's supersymmetric particles that are clumped out there that explain why those clumps of gases are out there in the universe, okay? So this might actually help us with our dark matter problem. At the LHC, we should reach energies where we can create these particles. If they're there, we should be able to see some of them. It's interesting. I mean, if it was a perfect, well, I could talk about that a little bit longer, but I won't. Okay. Another thing that's exciting, especially for some people in our group, is this idea of mini black holes that we could create at the LHC, Klaus in particular, the guy who likes the magnet and nail story. We could potentially make some of these events, but they'll decay very quickly in the detector, but they still might give us some insight into quantum gravity. And then the last thing that I'm going to mention is this large extra dimensions idea. And this is actually kind of fun. It might be that the reason gravity is so weak is that the gravitons that we haven't found yet actually escape into a different dimension. And that makes the gravitational force weaker. So if we create like a graviton in a high energy collision, the graviton might leave the three-dimensional world that we live in and escape into the extra dimensions. Now, we actually have some hope of maybe seeing this in our detectors because just like neutrinos, we wouldn't have conservation of energy and momentum. Something would be missing. We could have all the particles sort of going off to one side more than another. So we would have some hope of actually catching the fact that some of these gravitons were created. So this would help us also with, some of the string theories have large extra dimensions, and it would help us also with the idea of quantum gravity.
How do you distinguish a graviton from a neutrino?
That's a great idea. And it's a great the question was, how do you distinguish a graviton from a neutrino? And we know the processes through which neutrinos are created. So if you have an event, you can analyze your event and see if the other particles that are there match how neutrinos should be created. And if particle physics is really a physics of statistics, so you'd have to actually categorize large numbers of events and see that what you're getting out from your reactions can't all be explained by neutrinos. But you're right, that would be a hard thing to do. And we'd have to convince ourselves that we did it well enough. That's a good question. Okay. So thanks very much for listening. It was very fun for me to talk about it. And I don't know if there's time for questions.
So I'm sure there are loads of questions. I think we'll take a few questions here, and then afterwards we'll go outside, because outside there are cookies and other people. Sure, Sarah, would you like to?
Okay, I saw a white shirt hand up first. Yes, sir. Okay, so this is a question about the energies of a graviton being created at, what are people theorizing? I have to say that I don't know the answer to that question. I'm not sure. I mean, we haven't seen it at Fermilab, right, where we've reached, we're a factor of 7 higher in center of mass energy at the LHC. So I can tell you that we haven't seen it at Fermilab. There is hope that we'll see it at the LHC. So it must be on the order of a TeV scale in energy that we can produce the graviton. There are 4 detectors, and the 2 that are aiming after that kind of physics are ATLAS and CMS. LHCb and ALICE are doing different kinds of physics. Okay. Yes, sir.
I read somewhere where the LHC will be the first accelerator to test string theory, W boson scattering. Can you explain what that's
Okay, so the question was about string theory. I can tell you what I know about what parts of string theory will be tested. And there are two, I hope I remember both of them, that I'm aware of. One of them is the large extra dimensions, because some string theories, well, string theories in general require extra dimensions beyond our 3 dimensions normally, and then time, the 4th. They require up to 10, 15 dimensions, depending on your theory. So that's one way we could test it, probe for string theory. And the other is supersymmetry. It's sort of indirectly, but string theories require supersymmetry. So that's the other piece that we could go after. Yes, sir. Sorry, I'm clumping.
One of your early slides, you said that action at a distance was magical. I mean, all of this is magical.
Okay.
Why do you say that?
Okay. No, this is great. So the complaint was, all of this seems magical, but I put action at a distance in its own category. We really have the right to keep asking why is that happening that way, and how is that happening that way, and if these two things are interacting, what's the mechanism that they're using to interact? And in particle physics, we always have that particle exchange, which really does take away some of the magic, I think. I mean, that's the idea. If you have this particle that's going back and forth, I mean, what's magical would be 2 objects interacting, like one object appearing and the other object feeling a gravitational pull to it without, I mean, how does this object know that object is there? That's magical, without some kind of particle going between. I mean, it's really breaking it down to how could that possibly be happening and not being satisfied until you have some mechanism of communication. Well, other things bothered Newton that allowed us to get to this point. That's true. Okay, maybe one more question.
Do you have any opinion on that? There's been an experiment called mini-boom that has really caused people to wonder about string theory and symmetry. Do you have any opinion on mini-boom results?
Mini-Boon results. Okay, so Mini-Boon was really an experiment that came out as a result of another experiment. There was another neutrino experiment that was fairly controversial, had controversial results. And Mini-Boon came out, and actually they suggested, I had 6 quarks and 6 leptons, which you can separate into 3 generations of 2 particles. And results from the earlier experiment said, maybe there are actually 4 generations. Maybe there are 4 neutrinos, okay, which was sort of broke some other things in the standard model. So Mini-Boom comes along and tries to answer the question. My sense of the results are that they are not conclusive, actually, to be honest. That's my sense of the results. And I think there's a lot more that needs to be understood about them. But you certainly can get opinions from other people who are wearing the hats later. If anyone has a strong opinion on the Mini-Boon results, my sense is that they're not terribly conclusive. They certainly don't seem to point to 4 generations.